Good evening. Sorry for the delay. So today we want to talk about correlation. And it's very, very important to understand this concept because the way we use it in health research, is different from the way they use it, those people that are outside health. So sometimes you'll be hearing correlate. What they call correlate is different from the correlation. So when we say correlation, it connotes measurement, quantitative. Has something to do with something quantitative. So all this is that some people will just want to talk about if there's any relationship or any application, or maybe something has something to bear with something, just is very correlate. So those words in health research, we don't use it. That's why you hear something like correlational study. So you get to know the reason they call that correlational study. They also call it ecological study. Well, let's first understand this concept of correlation. If you remember, when we talk about those hypothesis tests, we say chi-square is test association between two categorical variables. T-test and ANOVA test association between a categorical variable, which is the exposure, and an outcome variable, which is numerical. A numerical variable, which is the outcome. That's both t-test and ANOVA. The only difference between ANOVA and t-test is that ANOVA, a t-test compare two groups, that is, mean between two groups, while ANOVA, many groups, more than 2, 3, 4, ANOVA. But it's virtually the same thing because the exposure is the group, number of groups, the group variable. While the outcome is that particular variable that you summarize as mean, which is quantitative. But when you see both, you are trying to look at association between both two variables, both of them are quantitative. They are not categorical, they are quantitative. In that situation, when we talk about in context of correlation, we don't actually talk about exposure and outcome, or maybe talk about dependent or independent variable. No, there's no one that is dependent. There's no one that is independent. There's no one that is exposure. There's no one that is outcome among them. Those are just two variables you just want to know. You know, when you are plotting graph for regression, you see y and x axis. The x-axis is the exposure, is the factor. That is the independent variable. While the y-axis is the outcome. The y is the outcome, which is the dependent variable. But in correlation, there's nothing like that. So you can put anyone at x. When you want to plot it, one can be if you want to look at correlation between height and age of a child, or weight and age of a child. So anyone can be on along y-axis, anyone can be on. There's nothing like this one determines this. Even though in real sense you may say this one determines the age, will determine the height or weight. But when you are talking about correlation, there's no dependent, no independent variable. We just want to know the degree of linear association between the two. Now, in everyday life, we use to denote some form of association. In statistical terms, we use correlation to denote association between two quantitative variables. We also assume that the association is linear, that one variable increases or decreases a fixed amount for a unit increase or decrease in knowledge. Just like if you say, oh, you are looking at association between the advert watch, and the number of advert watch, and the number of packet of goods bought. If You say it's linear. If the number of packets increased by 1, then the number of packet but will increase by a fixed amount. That is, if the number of you wash 1, you bought 3 packets. If you wash, maybe you now buy 6 packets. If you wash 3, you buy 9 packets. Can you see now? As one increases by 1 unit, a fixed unit, the other one increased by a fixed amount. That is the meaning of linear association. Linear association. Association is linear. So correlation is looking at the degree of linear association between 2 quantitative variables. Regression involves estimating best straight line. To summarize association, leave that one. Now, correlation describes the strength of association between 2 variables. Correlation is completely symmetrical. Correlation between A and B is the same as correlation between B and A. I'm just trying to tell you what I said before. So it doesn't really matter which one is x-axis or x-axis. If the 2 variables are related, it means that when one changes by a certain, the other changes on average by a certain amount. If y represents the dependent variable and x the independent variable, this relationship is described as regression of y on x. So when we are talking of dependent and independent, it's no more correlation. In that situation, we are talking of regression. But the situation where you just want to know no one is dependent, no one is dependent, that is correlation. So it's a measure of how much 2 random variables vary together. Similar to, so let's look at this. It's similar to variance. Sorry. In the sense that you can talk about covariance. How, for this is, I want to. So we want to look at concept of covariance from because the origin of correlation, it was this man that coined it, Pearson, the same person that first of all described chi-square. It was the one that coined the word standard deviation. It was the one also that described this word correlation. Pearson, Pearson was a genetist. Now, how did he do? Just like the way, I told us how he invented or discover chi-square from normal distribution. The same thing, how it described correlation from covariance. Now, a covariance is a measure of how much 2 random variables vary together. Similar variance, but it's similar to variance, but variance tells a single variable. Covariance tells 2 variables, how they vary together. If you say calculate the variance of, you can calculate the mean of weight. I calculate the variance, standard deviation. What the variance tells you for the weight is how the value of weight vary around that mean weight. If you do the value of y, of height rather, if you do the variance of y, of height, is how the value of height vary around the mean height. That's variance. But when you talk about covariance, if you want to know how do height and weight vary together, that would be covariant, because there are 2 variables and they vary. How do they vary together? As this one is vary, does this one vary with it? That's covariance. It's like 2 people moving together. How do they move together? So somehow similar to correlation. You're going to see that later you discover that correlation is a standardized covariance. So if 2 things vary together, and as one increases, the other one decreases, the slope will go down. That's what you see. First one. But if as one increases, the other one decreases, the slope will go up from left to right. That's the last one. But if there's no covariance at all, the thing will scatter. Look at it. You won't see on the line. Just scatter like the one in the middle. That's near zero covariance. Why the first one is large negative covariance. The last one is the third one, large positive covariance. Let's illustrate the concept of this covariance, how it was used to illustrate. Let's look at covariance graphically. The example I was giving the other time, if you want to look at covariance of the number of advertisement, how does it vary with the number of packets of product? So this is for 5 people now. This data here is for 5 people. So those 5 are designated as subject 1, 2, 3, 4, 5. Look at the number advert watched by them 5, 4, 4, 6, 8. And the mean number of adverts was 5.4. The standard deviation is 1.67. The number of packet bought 8, 9, 10, 13, 15. The mean is 11, and the standard deviation is 2.92. Now, if you are to show it graphically, look at it. We put both of them on the same graph. So each person on the point 1, 2, 3, 4, 5. So that last one is 5. You see the value is along the vertical. If you don't, the mean value for the number of advert words, when you look at the value of advert words in value, its K is smaller than number of bucket wash pots. So you see the mean number of advert wash is 5.4. Look at that line, blue is the mean that represents the mean. So the each value, what is the distance of each value from the mean? 2 of them has value above. Those ones that, okay, look at it. The first person was 5, and the mean is 5.4. So that's so that the value is 0.4 below the mean. That's why you see that dot. So the distance between it and the mean is 0.4. The second person bought a watch 4, and the mean value is 5.4. So the value is 1.4 below the mean. That's why you can see it has negative value minus 0.14 because it's below the mean. It's minus. The difference between and the mean is minus. When you remove mean from each value, the value that is less than mean will give you negative. Now, the third person 4 also. The fourth person 6. And the mean is 5.4. When you remove it, so the difference is 0.6. So that one's value is above the mean. The fifth person 8. When you remove 5.4 from it, it give you 2.6. Can you see? 2 of them have value above the mean. The other 3, the first 3, they have value below the mean. If you look at the number of packet bought, the mean is 11. Can you see? That's why you see that lemon green line. The mean of packet bought is 11. That's why it's below, between 10 and 12. So the first person 8 bought 8, which is below the mean by 3. That's why you see minus 3 there. The second person 9 is below the mean by minus 2 by 2. The other person 10 below the mean by 1. The fourth person bought 13 is above the mean by 2. And the last person bought 15 is above the mean by 4. Can you see? If you look at the diagram, you lay the thing at the flow for both of them. They are similar. If they don't covary, they covary in the same direction. You see now, these first 3 values, they were below the mean for advert words. And the first three value for packet bond, they are below the mean also. So the other last two value for both of them are above the mean. If let's say they vary in opposite direction now, what this one means that as the number of advert word increases, the number of packet word but increases also. They go in the same direction. But if let's say it's the vice versa, as the number of advert word increases, the number of packet word decreases. What will happen is that as those first three, the packet word, the advert word will be, those first three will be above the mean. So as the second, the last two are above the mean for the number of advert word, the other one will be below the mean. So they will be in opposite direction. If they still covary in opposite direction, that's what we call negative covariance. This one is showing that it's showing positive covariance. It says that they are in the same direction. If it is negative covariance, they vary also in the same in opposite direction. But if they don't covary at all, the thing will be opposite. Some will be facing, some will be you won't see any pattern. This one may be facing one another, this one will be away from one another, this one will be one direction. You can scatter anyhow. In that situation, there is no covariance. Can you see now? So it shows this covariance. You can use the logic. That is just to show it. What do I call it? Graphically. But let's look at it mathematically. Computing covariance. So if we say number of packet advert word, let's say it's X. The number of packet bought is Y. You just want to give them different. So the value of X number is signal. So you can break it down to say, okay, that X minus X bar square can split into two. X minus X bar and X minus X bar. Now, the one for Y, that's the number of packets is the variance sigma Y minus Y square X minus Y. You can break it into sigma Y minus Y bar Y into Y minus bar Y. The same thing. So their covariance will be, if the covariance is sigma X minus X bar to Y minus Y. Can you see that? The covariance you take one from each of them. That's what that is covariance. So if you compute it now, it will give you this value. For this, that's what I computed for this example. The advert was packet bought. But the problem with covariance, just like the problem you have with variance, is that it's going to be, if it's the size depends on the unit of measurement. If let's say you are talking of maybe X now, let's say you are comparing speed and distance, or distance and time. Distance and time. Spent. So where you measure distance in kilometer, time may be in hour. They are not the same unit. So the value you're going to have will depend on the bulkiness, the way the unit is. And the eventually also, the total size you going to have will also depend on the, well, you cannot say it depends on something because you are buying device. It depends on the unit. So in order to, let's talk about a line covariance can mean a strong relationship. However, you can't compare variance over data with different scale, like weight and cannot compare. A weak covariance in one data set is strong, one in a different data set with different scale. You use different scale. If you measure distance in kilometer, you measure in meter, you change to meter, it may give you different things. The same thing, time in hour, may give you different things. So the main problem with interpretation is that the wide range of result that it takes on to make it hard to interpret. So the larger the x and y, the larger the variance. That is that when you look at the scale, the value that comes with the scale, the bigger with the covariance. Similarly, the large unit of measure for y, the size of the unit of measurement of x and y, the larger the covariance, the larger the unit rather, the larger the covariance. So the intelligent people, well, person is the intelligent person behind it. In order to remove that problem, you remember something when we want to calculate z-score. Instead of us talking about, we said that the many things follow normal distribution, but the shape of the graph will vary. Though it may be the widespread, the contour of the graph will vary depending on the scale of the measurement. It may still be shape, bilaterally symmetrical, but the way the graph is will vary, and the height and the width will depend on the scale. Until somebody now say, okay, why not divide that difference in the way from the mean by the standard deviation? And that's what produced standard z-score. And that's what now produced standard normal distribution, which is only one. It has mean is 0, standard deviation 1, area under this graph 1. It's the same thing that person did here. It's not divided by the standard deviation. So you now divide the covariance by the standard deviation of x and y. When you divide the covariance with standard, it gives you correlation. So this formula for correlation is by bringing standard deviation of x and y and divide that covariance by the standard deviation, it gives you correlation. So correlation is a standardized covariance. So you standardize it so that it will be like z-score. It doesn't have units. It's become a ratio. It's dimensionless. You can just say correlation is 0 point this, but the value is 0 to 1. They can be negative or positive. Let's talk about it now. So the degree of linear association between two variables, that's correlation. The strength of the association is summarized by the correlation coefficient. And the coefficient is dimensionless. Quantity ranging from -1 to +1. So it's dimensionless, that is, it doesn't have unit. It's a ratio. A ratio is what you get by dividing two quantity of the same unit. When you do the covariance and divide by the standard deviation, both of them, they have the same unit. So it gives you a ratio. So if that is the kilometer and hour before, the what you divide by is kilometer and hour also. So kilometer cancel kilometer, hour cancel. So whatever you have is dimensionless. It has no unit. Just like z-score. So a positive correlation is one in which both variable increases and decreases together. Just like the example we see with this covariance, where the number of advert watch and they correlate the number or covary the number of packet bought. A negative correlation is one in which as one variable increases, the other one decreases. If let's say as the number of advert watch increases, the number of packet bought decreases. It's a correlation also, but it's a negative correlation. So it can be between 0 and 1, but because it can be negative or positive, so it ranges from -1 through 0 to +1. So it can correlation value can be any value from -1 through 0 to +1. When the variables are exactly linearly related, the correlation coefficient equal either +1 or -1. Depending, if it's +1, I mean that both of them vary in the same direction perfectly. If it is -1, I mean that both of them vary in opposite direction perfectly. Note that the correlation coefficient is unaffected by the unit of measurement. I've said that. The square of the correlation coefficient gives the proportion of the variation of variable of one variable explained by the other. I will explain this one. I will talk about it when we get to regression. This is what we call coefficient of determination. We talk about it. So you want to say that correlation and regression, they are related somehow. So look at pictorially. When positive, when you plot it, you go from left to up. At least at the y, the value of y-axis increases, the value of x where the value meet at the top. So you can see as it's going from left to right up, means that as the value of y increases, the value of x increases. The same thing with the second third. The only thing that it is patterning. So this one that is on one that is on a straight line is pattern 1 plus 1. Then when it becomes 0.9 not up to 1, you see some scattering. When you go 0.5, no, you see more scattering. In fact, if it's scattered, there's no direction. That shows that it's 0. So we see now when it becomes negative, that is, when as the y-axis increases, the x-axis decreases, the slope will from left to right go down. So you can see the value also for 0.5, 0.9 for minus 1. Minus 0.5, minus 0.9, minus 1. Can you see? Look at the graph below. When there's no direction, you can get correlation is 0. Now, this correlation, the one described by dividing covariance by standard deviation is Pearson correlation, because it was Pearson that first described this thing. That same Pearson, call it Pearson product moment correlation coefficient. Product moment is the way you get it by multiplication of 2 variables. Now the variance of 2 variables and divide by the standard deviation. Now there are other forms. You know, this one is only useful when you are dealing with continuous variable. But when that is continuous variable and you expect it's parametric, it's follow normal distribution. But when you see when there's skewness, it does not follow normal distribution, it doesn't work. So that's why many other people they not describe different type of correlation coefficient. Your Pearson is require interval ratio or data. It has to be either interval or ratio, numerical, continuous. Spearman, whenever we have rank, ordinal data. No, just know that we already said that correlation is not without number. You are looking at 2 variables. That 2 variables must be measured in number. That's their quantitative. There are some ordinal variables. Naturally, they are not number. But the number you give them is a rank. For example, educational level. No formal education, primary, secondary, tertiary. You can rank it 1, 2, 3, 1, 2, 3, 4. You give arbitrary value. What do you like SK? Strongly agree, neutral, disagree, strongly disagree. I'll give you value from 1 to 5. These are ordinary, they are ranking. Those are the ones we use whenever you use Spearman to do, because whichever we have ranked it, we have introduced number. And since it's not continuous, cannot use Pearson, use Spearman correlation. We have Kendall, it's the same thing, it's for non-parametric, but the Kendall does the same thing as Spearman, but it does it better, especially if you have tyrant. No, what I mean by tyrant? You know, when you run something, the tyrant means that majority in that data set, it's just like if you do like a scale now, where you have scale of 1 to 5. As if maybe almost everybody is 2, 2, 2, 2, 2, 2. Disagree, or 4. Yes. Agree, it's more. So that's what we call tyrant. So when you have too much similarity, tyrant. candor does better than spearmint. Now, there are two concepts that are very, very interesting. We call it point biserial correlation and biserial correlation. They are very intuitive. This point biserial correlation, number 4 on this table, it quantifies association between a continuous variable and a discrete dichotomous variable. Point biserial, discrete dichotomous. That is, there's no continuum underlying the two categories. Why the biserial? Anyway, I wanted to ask, maybe somebody can say, don't let him bother you. When we say there's no continuum, look at male or female. Let's compare with the second one, the biserial correlation coefficient. It quantifies association between a continuous variable and a continuous dichotomous variable. That is, there's a continuum underlying two categories, passing or failing. You know, when we say continuum, when we say by dichotomous, mean that there are two possible yes or no, alive or dead, or whichever. Yes or no, male or female. When there are only two possible outcomes, that is dichotomous. So what is the difference between the discrete dichotomous and continuous dichotomous? A continuous dichotomous, when you say failing or passing, you know, before you can see somebody fail or pass exam, you will have had a score, and they will not say there's a cutoff. If anything below 40, 40 and above is pass. So that passing, whether you classify somebody to pass or fail, is based on a continuum. There is a numerical variable underlying it. It's just that when you say somebody is anemic, it's the same thing. It's a continuous dichotomous variable in the sense that it will do hemoglobin concentration or PCV, and have a cutoff that anything below this one and above is normal. Anything below this is anemia. Anemia, yes or no? Anemia, no anemic. It's a dichotomous variable. It's a continuous dichotomous. It's the same thing with blood sugar, diabetic or not diabetic. Because when they do blood sugar, they say anything 126 milligrams per day is diabetic. The other one, not diabetic. So just like say you are hypertensive, systolic hypertension. So 140 and above, systolic hypertension. Below 140 is normal. Hypertensive, intensive, no, yes or no. Can you see all those things? They are continuous dichotomous variable because there are some underlying continuum, that is underlying numerical variable that you set cutoff for. I give you that. But for the other one that is discrete dichotomous variable, there was nothing like that. Like male and female, there's nothing continuous behind it. Alive or well, dead or alive, there's no continuous around it. So now, when you have one continuous variable and one discrete dichotomous variable, the one that has no continuum, you do the correlation. We call it point biserial. You may begin to say, how do you give the number? You give one number 1, the other one 0. So out of the two options, dead or alive, you code one 1, the other one 0. That's why you correlate it with that continuous variable. So for this other one that is continuous dichotomous variable, of course, when you have set the cutoff, so we call it there. So you have, when for example now, you see the correlation between age and diabetes is a partial correlation, because without diabetes, yes or no, is a function of the blood sugar they have done. And whereas the age remain, or the weight, or whatever remain. So that type of correlation will be a biserial correlation. So this is testing, this is sperma. You know the difference between them and anything. So to compute correlation is very simple. So you may not be interested in that. compute it, see the way. One is just the formula. In the formula, you need x minus by x. You need y minus by y. So you need to multiply the two. Anyway, once you get x minus by x, y minus, you sum them. You multiply them and sum them. Then you need sigma x minus x by x squared with their square root. Can you see all those? So if you look at it in this table now, you already generated them. We have x, y, x minus by x, y minus by y. Then multiply both of them. Then x minus by x squared, y minus by y squared. When you generate it, you put it, sum them together, do the correlation. Then don't bother yourself. This person, this is his own formula. Spearman. No. This one is t-test to test the significance of the correlation. It's useless. To tell you the reason. Spearman, different approach. Then his own, the plot of data may be revealing some, I've already explained it. Plot of the data may reveal underlying point away from the main body of data. That is when there is outlier in that situation or the other category, you use Spearman. And this is your same formula. R equal to 1 minus 4d squared over n minus n squared. So once you do this, can you see? You put all those, these are the same example. You just calculate all these things. But you need to bother yourself about that, just for you. So there's other form that I don't bother with that. PEMDAS, power correlation, so remote. So there are many of them like that. So what last thing I want you all to discuss here is how do you interpret? You notice that you use theta to see the correlation is significant or not. Well, the computer will give you, but it's even useless. We don't interpret correlation using p-value, and the reason is very simple. Sample size affect the value of the p-value. If the sample size is very large, small correlation will be significant. Small correlation will be significant. If the samples are less, for example, now you have 400, 200, something large. Correlation that is 0.1 or 2 may be significant. But if the sample size is very small, even large correlation may not be significant. If the sample size is very small, it may not be significant. Can you see now? So you see, when you see significant now, it now depends, it's not a matter of where the value of that correlation is the sample size. And that is why you don't use sample size to interpret correlation. So many people devise different way. You see. They say, look at this one. If it is 1, perfect. If it's 0.7 to 1 is strong. If it is 0.5 to 0.75, moderate. If it is 0.25 to 0.5, weak. So it can be on positive or negative side. Yes? But look at the one up here, another person, which make him more a little better. Is one I'm happy to use. When the thing is less than 0.1, negligible. From 0.2 to 0.4, low relationship. 0.4 to 0.7, moderate. 0.7 to 0.9, high relationship. 0.9, greater than very high. If it is 1, it's perfect. So that's why we say, oh, there is a strong positive correlation. So that's the interpretation. You using p-value. It's not used. But some examiner don't know. P-value, we put a p-value. So I think we stop here. Some other thing on this. Some other thing. There's no point, just to understand the simple concept. I don't know if there's any question. Any question? It's just three of us that are maintaining. Dr. Sebastian. So any question? It's very simple, right? It's straightforward.
Well understood, sir.
Thank you, sir.
Yeah, Dr. Clement.
Yeah, well done.
Good evening. Well done.
Thank you, thank you.
After I will call you, there's a training workshop I'm organizing.
Okay.
Well, I will call you with discuss it.
Okay. Well done. Yeah.
Okay.
Yeah, good night. Good night, everyone. Dr. Nonju, good night. Dr. Idiro, good night. I will share it on
Good night, sir.
Good night.
Okay, thank you so much.